Our next presentation comes from Dr. Jeff Hammond, research scientist at Intel Labs in the Parallel Computing Laboratory. Previously, Dr. Hammond was an assistant computational scientist at Argonne National Laboratory and a research fellow of the Computation Institute at the University of Chicago. In 2009, he received his PhD in chemistry from the University of Chicago's Department of Energy Computational Science Graduate Fellow and holds degrees in chemistry and mathematics from the University of Washington. In 2013, Dr. Hammond received the inaugural Young Achiever Award for the IEEE Technical Committee on Scalable Computing. Today, Dr. Hammond will present on code portability and abstraction tools. Dr. Hammond, thank you for joining us today. You may now begin.
All right, so I'm Jeff Hammond. I work for Intel. I'm going to talk about SYCL and data parallel C++ for GPUs, and then I'll elaborate on beyond GPUs, but that's the focus. So the motivation in my mind for standards-based GPU programming is the diversity of architectures. So I was in DOE 10 or so years ago when the DOE kicked off its EXASCALE planning and R&D exercise, and back then they said, okay, one of the swim lanes is an IBM Blue Gene thing, and the other swim lane is a GPU NVIDIA system that looks like Titan. And of course, that's what the leading systems were at the time, so it made a lot of sense to start there. What's interesting is here we are at the cusp of EXASCALE, and the DOE at least has chosen to do something different. Obviously, many core, the CPUs now have more cores than Blue Genes did. But they're not many core in the way the Blue Gene or Xeon Phi are. They're big core servers. And of course the GPUs are different. They are GPUs, so that was a safe prediction. But they're GPUs from Intel and AMD. And so it's natural then to look at this and say, okay, what were the right software models if you had a crystal ball in 2011 to plan ahead for EXASCALE? What would you have done? And so I'm going to talk a little bit about SYCL, which didn't exist in 2011, but is, I think, a very compelling model for trying to go across multi-decade programming challenges as we look forward. So the other systems, of course, that still matter. In the U.S., there's going to be a big NVIDIA-based supercomputer at NERSC, or partially NVIDIA-based. It'll be some CPU only, some CPU, GPU, and then of course there's the biggest NSF system. Is Frontera, which is all Xeons, and then there's of course the #1 system in the world, which is Fugaku, which is an ARM, probably the closest thing to a many-core that exists today at the top scale. And then lastly, and I think this is really important, but often neglected in the context of big iron HPC that people want to get jazzed about, is the fact that a lot of science, a lot of real science, real data analytics, real simulation is done on people's laptops, and it's absolutely essential that we have software that go across all of these systems. It's not sufficient to just have software that works on 1 or 2 GPU architectures or all the GPU architectures, but no CPUs. And there are other things out there, FPGAs, ASICs, and all sorts of other fun things that are coming down the line that people might want to program. But I will continue to emphasize that, if you can't write code for a supercomputer on your laptop, you're going to have a bad time. And I will, even though COVID has, of course, canceled all the flights and all the trips, I still remember writing a significant amount of serious HPC code for supercomputers, flying on airplanes without internet connections, and in my Mac terminal. And I was actually able to write code for, Intel GPUs on my Mac laptop because I was writing in standards that work. So finally, and this, I won't get into too much detail. I have a talk online I'll point to at the end. But I think another thing that's really important as we look just at the GPU supercomputers is that things have changed relative to where we were in the beginning of the GPU era. The first big GPU system was Titan, which was 1 AMD CPU and 1 NVIDIA GPU. And that, kind of kept things simple. You had 1 NIC, 1 CPU, 1 GPU. If you, didn't spend too much time thinking about how the cores, interacted with the GPUs, then, you could kind of think everything was 1-to-1. But this is no longer true, in part because of power and Linpack and AI, people are, making these systems what I would call top heavy. So they're very GPU intensive, and obviously they have more cores than they do GPUs. But certainly, all of them have at least 4 GPUs at the high end, and I think that will continue because once you sort of buy into the GPU idea, it makes sense to just push a lot of the work onto GPUs and make the CPU kind of a helper. If you can do it, doesn't always work. But I think this is a really important thing for programming models is if you have a GPU programming model that doesn't work really, really nicely with multiple GPUs per process, per thread, or per node, however you want to slice and dice it, you're not going to be able to use these next-gen systems effectively. So the SYCL ecosystem for GPUs, not the full SYCL ecosystem, is, there are 3 compilers with different facets to them. So the Intel Data Parallel C++ compiler is part of one API. A lot of folks, I think, have heard about by now. So there's a product compiler ships like Parallel Studio. It's based on Clang LLVM fork, which is open source, and they are largely the same. It's not like there's 2 different compilers. It's a productization of the open source version, obviously with some QA and a specific Git hash, so maybe they're not identical at every day of the week. But there's a lot of features that were put into DPC++ prior to standardization. I think that's a really important thing. It's something I've observed for years in the MPI standard. It's really, really critical for implementers to get out ahead of the standard and prototype things so that they can be standardized with confidence that they're actually good ideas. Standardizing without implementations is a fool's errand. So DPC++ supports all the Intel hardware, so CPUs, GPUs, and FPGAs. And it also supports, in the open source version, NVIDIA hardware. CodePlay, which is a company in Edinburgh, did that work, and I've been using that recently too. So that exists. This is not an Intel-only solution, and there's certainly the opportunity, because it's open source, for a lot of people to contribute to it and do other things. I will also add that I did some work to make sure that the DPC++ compiler works on ARM. So I ported it. It works on my Raspberry Pi. It works on Thunder X2. I'm sure it works on A64FX, although I have no idea how well quite yet, although I'm sure that Simon will tell me someday. So second major compiler, so CodePlay's product compiler, which is available as both commercial supported thing, which is fantastic if you're a serious person and need serious support. They also have a free community edition, which is a wonderful service. And so they support two sort of versions of their compiler, or two backends. It's one compiler. So the OPENCL SPIR-V device family, which includes Intel GPUs, but also other things. And they also support an NVIDIA backend with PTX, and they use the OPENCL runtime in there. So I've used both. I've used those on NVIDIA for well over a year, and also on Intel stuff for over a year, and I use that on ARM too. So that's another compiler that has multiple hardware families in it. And then finally, there's a wonderful project out of the University of Heidelberg called HipSYCL, developed by talented fellow named Maxwell Alpay. It's on GitHub, so it's open source. It's based on what NVIDIA would call CUDA or CUDA Clang, the GPU support in the LLVM Clang stack that HIP is based on. So they're building on that, and they build a HipSYCL is a tool chain that puts SYCL on top of that, and so it means it drops into either the CUDA path or the AMD GPU path, and they also implemented an OpenMP CPU path. And I will say, very recently, they've picked up some of the soon-to-be standard extensions that Intel developed, including unified shared memory, which I'll talk about in a minute. And of course, Intel's really happy to see this, and very recently we announced we're sponsoring them because we think it's really important to have the features that were first implemented in DPC++ widely available, not just standard, but also available on lots of platforms, because having standards without implementations doesn't mean much. So it's a very good question to say, okay, well, there's all these things that exist. Do they actually work? Is this serious? And I will say, please don't take my word for it. I really prefer to cite, third-party non-vendor sources for things like this. And of course, Tom Deacon and Simon McIntosh Smith are very trustworthy sources for performance portability evaluations. This is their work. Obviously, it's in the IWACL conference, so the paper's online, the video's on YouTube, and you can check out the code. And what they've shown here, obviously, for Babel Stream Triad, which is a lot like the Stream Triad in C++, is for AMD, for NVIDIA, for Intel GPUs, you see that the SYCL programming model is roughly equivalent to the vendor's preferred model. So on NVIDIA, you've got CUDA at 90 and SYCL at 86, and on AMD, you've got plus or minus 1.5%. On Intel, the difference is very small because, of course, we're not developing a proprietary stack off of this. We're just developing SYCL directly. There's an issue on Xeon. It's a compiler bug in one of the OpenCL compilers. I think actually if you use HipSYCL with OpenMP or something else, it'll probably be just fine. But that's just an example that for memory bandwidth, which is extremely important for CFD engineering type workloads, SYCL gives a very compelling performance portability. There's another great study out of Argonne. Brian Homerding has done a lot of work on the Livermore-Raja programming model, and he's implemented a Raja perf, which is sort of a 21st century Livermore loops type test bed with a lot of different physics kernels in it. Some of them are simple, some are complicated. You can see rotate your head 90 degrees and see what the kernels look like. All the details are of course online in the link shown. But this is, I think, pretty interesting because you see the red and the blue curves are showing the relative performance, and all the lines are not on one side of the zero axis. So it's not universally true that CUDA is better and SYCL is worse. It just so happens that because you write different code and you have different compilers and different optimizations happen, you can end up on both sides of the curve. So obviously somebody in NVIDIA could sit down and tweak the compiler, tweak the code, and beat SYCL 100% of the time, because you can always beat a portable model with a non-portable model given infinite effort. But this is somebody who's a smart programmer working in a national lab who has no interest in cooking the results, who wrote the code and did a good job and found that obviously you can win and lose with standards. And that's a really fantastic thing to see, that maybe on average you break even without compromising portability. So let me elaborate on what DPC++ is in case there's any confusion. So there was SYCL 121 is the latest ratified standard from the Cronus group. And that existed before Intel got involved in any of this. CodePlay was the first implementer. Xilinx, Ronan Carroll was involved a lot in this too. Intel joined up with this effort and started contributing to what is now the SYCL 2020 provisional spec, which included a bunch of Intel proposed extensions and, of course, extensions from CodePlay and others. And then DPC++ will continue to develop extensions. So it's natural to ask, are we committed to standard? Yes, absolutely. That's why we've contributed every single one of our extensions for GPUs to the Cronus community and working with them to both standardize them and adopt them. But we're going to continue to develop extensions, obviously, to understand what the right way to do things is, because our customers say we need these extensions and we don't care about waiting for standards. Give it to us now, which is a perfectly reasonable thing to say to a vendor. And we expect the standard to be sufficient, but also, like we did with the extensions we contributed before 2020, they were there because customers had a need and people thought they were a good idea. So all of the extensions we're working on have been implemented in the GitHub version of the compiler and are documented on GitHub. So there is nothing proprietary or Intel, parochial about them. They're just, it's just that Intel is doing them. Just like, if we contribute something to MPitch, it's out there and other people can have it. So why did we do SYCL? So there's a lot of different ways you can approach GPU programming. You could say directives, or you could say kernels, you could say proprietary, you could say standard. We decided that we really wanted to do something that was standard. We wanted to build off of an existing ecosystem. Obviously, OPENCL has been well established for many years, and there's a lot of good things about it. It's portable. It's a good execution model. People thought really hard about it. It's robust, and people have thought about corner cases and semantics and written them down in a precise document, and that's really good. On the other hand, there's a lot of people who find OpenCL rather verbose. They don't like the host code or whatnot. And there's a bigger issue in sort of the more recent years where modern C++ has really become a fundamental part of HPC programming. And we want a programming model that actually supports modern C++ properly. And OpenCL has some integration with C++ on the host and the kernel, but it's not holistic. So SYCL is based on purely modern C++. It's really starts at C++ 11 and goes from there. So it's not, catering to people who want to think about C89 style design. If you want that, you can have OpenMP. And by leveraging modern C++, it allows a lot of good syntactic expression. It's also similar to TBB, if you like TBB, or to Parallel STL in C++, except it's explicit about hardware control, and that's really, really important. And I'll show examples in just a second. So SYCL is really the first programming model that's trying to be a standard for heterogeneity and C++. So there's Cocos out there and Raja, which are open. They're not standard. They're not writing a standard documentation. Standard document. It's more just a standard reference implementation that everybody can use, and it's a community effort. And that's a great way to do openness, is to have a community and a reference implementation that everybody contributes to. There's also value in having a standards document from Kronos and then having multiple implementations. And as we've seen, there are, multiple different compilers implemented out there, and it's really nice to have, just like we like having GCC and Clang and ICC and PGI and Cray and Fujitsu and all the other compilers. It's great to have a lot of different compilers with people thinking about different ways to do things. And of course, then, like ISO languages, having a standards document to refer to. So this is the full ecosystem. I already mentioned some of this, but the thing I'll also point out here is that it's not just GPUs and it's not just CPUs. There's FPGAs. I've actually run Intel FPGA code with SYCL. I'm not an FPGA expert, so I ran something trivial. Ronan Carriel is an FPGA expert, and he works on the Xilinx stuff. I don't have Xilinx hardware to test that, but I trust Ronan. If he's doing this stuff, I assume it works for them. And then there's also the work that CodePlay has done with ARM GPUs, which obviously are more relevant to phones than they are to supercomputers, but still another demonstration that this is a portable programming ecosystem, as well as Power VR and a car. So you can program everything from your phone to your car to your supercomputer with SYCL, and I think that's lovely. And I really don't think there's anything else out there that has the breadth of hardware support and deployment demonstrations that SYCL does. So now switching to code to motivate some of the stuff of why SYCL is cool. So this is an OpenCL program. You can see there's a couple of things here. One is you've got the kernel and you've got the host code, and they're separate. And a lot of people don't like this. They don't like the fact that OpenCL kernels are either external files or strings, whatnot. But the host code is also a little bit tedious, even with the beautiful C++ wrappers that folks in the Kronos community created. Why you have to tell it to load a kernel and make a kernel, it's there, it makes sense, but it's kind of a compiler target rather than a user model. So we see the same thing in CUDA. CUDA is a little bit more compact because it's obviously targeting one type of device, and therefore it doesn't have to tell you, to tell which device to run on. It's just going to run on the CUDA device. But it's got the same separate compilation model, which I personally don't like because I like to read code top to bottom. And it's also got, maybe it's a little bit explicit, and it's certainly not super C++ friendly in the traditional form, at least. So this is SYCL 1.2.1. There's a little bit more code here, but the nice thing about this code you see right away is there's only one. You read this top to bottom. There's only one source. So key features here. There's a GPU device selector. So you got to say, I want to run on a GPU. You can also say, and this is really important, I want 4 GPU devices. So if you're on one of those massive 40 teraflop GPU node things that is mentioned, then you want to be able to control each one of those devices separately and submit work to it, and you can obviously do that with explicit devices and queues. So there's buffers and accessors. This is the part that some people like and some people don't like. So it's a really nice way to create data flow graphs and allow the runtime to do good data movement for you, so you don't have to write those copies. But the bad news is it's not pointers, and some people really, really like pointers. Finally, so this is the parallel 4. So this is the kernel. So there's no long jumping or split window editing to have your kernel off in some other place. You don't have to worry about whether or not you've matched the arguments and waiting till it seg faults at runtime. You just write the kernel where you want it in the code as if you were writing OpenMP or parallel STL. And I think this is really a huge benefit to programmers, is not having a split source development model. And I'll get into a little bit more of this, but there's a range on the loop and there's a kernel name, and the kernel name is optional, but it's there for tooling reasons in some cases. So here's SYCL 2020. Obvious thing here now, we have pointers. So you have SYCL malloc shared, and this is kind of like CUDA unified memory or OpenMP unified shared memory. This thing can move around, so you can allocate it in. It will be either on the device or it'll be on the host, and then when you touch it, it'll move. There's obviously other controls, so there's a malloc host and a malloc device if you want more control, and then you do mem copy. So it's a whole lot like all the other GPU models that are explicit for people who really want that. You could say, okay, well, this is nicer. It looks more like the GPU models, but it can get better, and this is something that simplifying this kernel part with this submit and parallel 4. Like, why do we have a handler? Well, we don't need one. So it turns out you can just remove it, and this is nothing more than trivial C++ header magic. And so now we have, if you read this top to bottom, you say, I want to run on a GPU. I want to create some buffers that can move between the host and the GPU. I have a parallel kernel I'm going to run against that GPU queue. I'm going to wait for it, and then I'm going to free the data. So this is, I think, the absolute bare minimum syntax you need to express what you're actually doing here. I think it's really compact. There's one line of code for every concept that you really need to understand, give or take, except for the loop body, which loop bodies are rarely one line anyways in complex stuff. But so this is about equivalent to what you'd write in OpenMP or Cocoa. So I think it's quite compact, and I think it's pretty nice. So I don't actually know what my time is, but I wanted to just point to some additional resources. There's a lot of stuff out there. I sort of prefer to cite stuff that I've actually used and read, just to have higher confidence. So I wrote a simple tutorial that shows SAXPY, which is HPC Hello World, with buffers in USM that runs on Intel and NVIDIA, including the USM stuff. We fixed a silly compiler bug last week or two to get that all working. There's a nice intro from Federico Ficarelli at Chinica talking about writing GPU code with SYCL. He goes into some of the details of the data flow graphs and buffers and whatnot. Argonne has a very nice SYCL tutorial that walks you through stepwise some of the different concepts that are out there. There's some stuff I did recently with the Livermore Quicksilver mini application, which is Monte Carlo neutron transport. So this is kind of a hairy beast. Monte Carlo neutron transport is not simple. There's a big, deep nested hierarchy with lots of branches and lots of indirection and particles flying all over the place. And this is a cool study from my perspective, because I could have ported the thing directly, but I decided to use it as an exercise to play with the DPC++ compatibility tool, which you can read about more, but that's basically a tool that helps you migrate code from CUDA to SYCL. Some people, look at SYCL and say, well, I don't know if I want to go all in with this. I'm not ready to commit and do all the code writing myself. Make my life easier. So this is a tool. It's not like a HIP. It's not a Perl script. It doesn't just magically change namespaces in your code works. It's a tool that tells you about here are the things that need more work, and here are the features that are not a one-to-one match. And then for other things, it can provide the appropriate template on what to do in SYCL. And so it took about 4 hours. And that was 4 hours while I was also in meetings. So it really wasn't difficult at all. And then I went through and I cleaned up all the code and because I'm a little bit obsessive about code style, and got that working. I've actually run that on an NVIDIA Pascal recently, and I'll run it on both next time I build a compiler. So that's a code now that I wrote on a Haswell or a Skylake generation NUC, and now it runs on an NVIDIA Pascal. So that with zero code changes. There's another example with Bright Skies. This is on GitHub. There's a nice write-up. This is for seismic RTM, which is an important application in the oil and gas community, among others. Finally, there's James Reinders has a DP++ book that he's working on with some Intel folks, and they've got some code online and some tutorials. And lastly, there's SYCLETech, which is I think Rod Burns maintains it from CodePlay, and he's got a lot of great resources. Some SYCL summer talks a couple weeks ago, including the one I gave, which has more details on the multi-GPU programming angle. And then lastly, if you're really interested in the OneAPI details, oneapi.com has links to all that. And I didn't talk about it all here, but one of the reasons that OneAPI matters in this context is direct programming is really important, and you can't program GPUs unless you have a GPU programming language. But that's just the beginning. You also need libraries, you also need tools. And so what OneAPI is about is building out that library ecosystem. So, it's not like the early days of OpenCL when it's like, okay, here's OpenCL, that's great and all, but where's my BLAS library? Oh, it's not there. Where's my FFT library? It doesn't exist. OneAPI is actually bringing the library part of this for deep learning and whatnot. So that you can do API-based programming, which obviously in the AI era and on a lot of HPC codes is really, really important to have those libraries as well. So please check that out. All the OneAPI stuff is at least open specification, so there's no propriety in the API, and many of the APIs have open source implementations, but that's by no means required. And CodePlay has actually done some work to port the OneMKL BLAS interface to CUDA BLAS, which of course is an open source, but it's really nice, of course, to be able to write DP++ SYCL code on an NVIDIA device, but to also be able to call DGEM and whatnot. So anyways, that's the end of the talk, and hopefully I've left some time for questions and discussion.